Hello everyone. Uh, Welcome to week problem solving session. And this session will be solving some problem related to some plant mechanism and some problem also related to the sensors, the actuators type of actuators, and also related to different types of mechanisms, like not mechanism but basic sensors and basic actuators are used in disk drives. As you can see, assignment 3, uh, most of the problem are related to you can mark multiple correct answer options, and start the session. So these are the problem which I am discussing. These are the questions which are asked in the last year problem. The solve this problem. Okay, I mean I know some of the problems won't cross in the assignment, but these problems are last year's exam problems. So careful with these. First question is related to the spring mass measuring system, right? Spring. So here is the question: the spring based weighing system, and these are your options. The question it is given that you have mass uh, spring depending upon the stiffness. How much the mass is high, then this pointer point a little lower. Is uh, so this is 0 kg, 100 kg. Higher mass than due to will deflect, the spring will deflect more, right? The mechanism, and your question is which of the, suppose if you have a high stiffness spring here, uh, will gives a force resolution or a large range, or and if it's a low stiffness spring, it gives a force resolution or a large range. This is your question, and you need to answer which one of them is true, right? Now to solve this type of problem, we need to know what is resolution and range. Okay, let me just try to. So like there are two problems, right? High stiffness and low stiffness. There are vice versa. There are multiple choice that are being valid. So just first of all, let's look into the draw both the cases where the stiffness is high and where the stiffness is A, which is high stiffness. There are two. Here A is the smaller one. A is higher, so it's a high stiffness. I think I think you know the basic formula, right? B F A. If you have a high stiffness K, that can take higher forces. If you have low stiffness K, can take lower force, right? I think you know that basic, right? How high stiff is, it can take higher load, right? But here the case is different. Here we have first of all, let's look into range. What is range? Range is like basically how much mass can carry. It can weigh actually. So if it has a higher mass. It can suppose this one. We have a small mass M, we have a capital mass. So range is basically capital M minus small m, right? Uh, right. Suppose this is a high stiffness peak. Suppose if you put a smaller mass here, right? If you put smaller mass, then what will happen? It will deflect, right? But it will deflect very less, right? And if you put this higher mass, it will deflect. It will deflect more because of the stiffness. So if you see this, it can measure small mass also, right? Just need to put, but it will deflect very small. But in this case, so I'm talking about the first of all range here, right? And if you put the this is a small low stiffness, right? If you put smaller mass here, it will deflect something like up till this. Okay. If you put same mass, the bigger mass here, it will remain the same because the scale itself is not long enough. Okay. It will deflect more, but the capacity will be over. So it can take to the scale, right? So if you put a small mass, then also it will deflect like up till here. If you put a higher mass, then also it deflect like that. So there is a some kind of a range. So can't suppose if I want to put a bigger mass like this this weighing machine can take it with higher K, but this won't take. I mean, this will take it, but won't show you the true value, right? Because the K is very small here. Okay, so for a low stiffness spring, the range here will be very small. Can't a low stiffness spring, it can't take higher range masses or higher. Can't take very high large ranges or higher masses, right? So you see the options. So if high stiffness, then it can take high. So these are your this right or high stiffness, high stiffness. So this will be wrong because it's a low range, right? So this can so these look the good option. And let's look into the and if you see the low stiffness one, you see low stiffness, low range, right? I told you can take up to a low range masses. This is right. Okay. And so yeah, so these two are right. Let's look into the resolution. So what is resolution means? Resolution is smallest mass, the smallest change it can measure. Okay. Suppose if you have put some kind of a same mass, okay, small m, and if you put small m here, and what you want to do measure is resolution. So resolution, you measure resolution by incrementing a small change. Okay. So if this is a small m, suppose 0.01 m, very small. It's like 1% of m. If you added here, okay, because the stiffness is very high, it won't the scale won't even change. It because I mean because it's a high stiffness here, because the scales are aligned like that. But if you again put the same mass in this second case, because the stiffness is very low, it will deflect slightly. Okay, zero point zero 0.01 mass, which means that it has a higher resolution, right? Higher resolution means it can measure very fine measure. Higher resolution means the fine resolution. That's what fine. It can measure very fine measurement. So the smallest, as small as 0.1% of the small m can be measured. This is called a small. So the low stiffness can measure very small measurement, which is called fine resolution. So it is a fine resolution. So the option is here is right. Whereas in this case, if you put that small 0.01 m, it can't measure it. Okay, well, it won't measure it. It can measure if you put something kind of a m here, but it will measure that, but it won't measure 0.01%. It, it has a resolution, but it has a coarse resolution. So here option A and D will be right here. Okay. So this is how you need to solve this kind of a problem. And then there is a match the following. Match the following. Yeah. So you need to match the left hand side. You have the motors, and in the right hand side you have the application for the motors. What the motor why those motors. The left side is the motor, and the right side is the motor application. So if you see, the first one is a BLDC motor. So BLDC motor basically we can use for many more things. But here in this case, for CD-ROM Sindel, I think in the last problem solving session, I've told you that CD-ROMs are being run on the constant velocity, right? Constant velocity. So BLDC motor can only do this kind of stuff. I mean, you have, I mean, I think my last lecture, you have this C, uh, CD, and this is the rotor. At every peripheral point, R, R1, R2, R3, the velocity will be same. Okay, so V equal to omega R. Okay, so V has to be velocity equal. Yeah. So this is how you velocity remains same, not omega. Omega can vary and R can vary. Velocity needs to remain same. That's what the matter. So this can only be done by this BLDC motor. These are high power. These are kind of intelligent motors. Okay. So A option will be A option answer will be C. Then stepper motor. Stepper motor, I think Professor Gandhi has told you about stepper motors. You can use in scanners, and if you remember, you can also use in for that. I mean, for moving the photo diode. And then there is a physio actuator. So physio actuators are basically used for just left physio actuator. I will that for last. So if you see hydraulic actuators are used for, I mean, these are very high powered actuators. So forklift is the application which you can. Voice coil actuators. So voice coil actuators, I think these voice coil actuators are used in hard disk drive motions, and I think piezo actuators are used in inch form motors. The option will be something like 5A. So this is what your correct answer is. And let's come to the, so the last three class, the last 3 weeks. Very rare that you will get some numerical question. It's very rare because I mean, if you gone through those assignment, there is only, I think this is the first this is the first assignment where you can get a numerical question. So these questions, I mean, the questions on compliant mechanism are one of the important question which can come in exam. I would extra force on them. So please try to solve these questions, okay, and please try to remember what are the principle on which it works, okay. This is a simple compliant mechanism. You can see here it is a compliant mechanism made by a EDM machine, by EDM machine. So some kind of a, using a EDM machine, they like cut down this middle part, and this is a kind of a cantilever beam, and you can see 35 mm thick slab. So it's a 35 mm thick uh, outside the beam. And if you see Young's modulus is 130 gigapascal. So your question is using Euler-Bernoulli beam theory, first calculate the stiffness of the beam. So please do remember it's a compliant mechanism. Okay, so please don't solve this question by like you solve your in your, I think in the second year of mechanical engineering. For that, in that case, the boundary conditions are different. So it's uh, a point weight cantilever, single point weight. Yeah, it's an end point weight cantilever beam question. These are different. So please do remember it's a compliant mechanism. Okay? So the boundary condition will be different here. So first of all, let's look into what is Euler-Bernoulli beam theory. So this is what Euler-Bernoulli beam theory looks like. So this is the differential equation or the governing equation on which the whole beam theory works on. See the Euler. there is one more theory, but here we are using Euler-Bernoulli theory. So which is, so here like a differential equation and differential equation, fourth order differential equation in displacement y is the displacement and x is uh, the distance from a point, which is, and see this problem is this so if you see this is simple mass, not a problem like which you have heard. It's not a something like this. It's not a point mass. It's a distributed mass, but it's distributed only up to this point. So if you, so how to solve this kind of a problem? So what you need to do is just need to cut out, because there are two uh, like slabs are there. There are two thick slabs, right? First, what you need to do is first you need to like this and divide the whole mass by two, because yeah, that is because it's p by two, and again if you add it, then right, p by two. If you see this part and if you integrate this part, this is a distributed load. Here we don't have the distributed load, right? Like here we have a kind of a shear force. So if you integrate this part, you will get a shear force, and you know that the shear force is F by 2 at every point. You draw this MD, and there is a SFD with shear force diagram. Look like this, like like this, by 2. So this is, and based on different boundary conditions, you need to solve the stiffness of the beam. Stiffness is basically F by K or F by X. First, you need to solve, if you, in order to find K, I already have force. You need to know what is the displacement. First, we will calculate displacement, right? And in order to find the displacement, which is Y, how to solve this kind of equation? You need to integrate this stuff, right? Not integrate, so you need to integrate three times. If you integrate three times, you will get three constants, right? So if you integrate once, like F by 2 x, right? If you integrate twice, you will get x square by 4 plus 1x plus c2, right? Yeah, so if you, when you integrate twice, you will get up to this point, okay? I mean, up to this point. So you need to solve for C1 and C2. So what you can do is you need to apply this boundary. So this boundary condition where deflection at x equal to 0 and at y equal to 0 are 0. Okay, please do remember this boundary condition. Okay, so this is only apply for a compliant mechanism. So what it means is that when you apply this force, what will happen? The beam will bend like this. Okay, but there is some kind of a mass here, so it will, is a, will look like this. Okay, and if you see the deflection part, here the deflection is 0. If you remember, this is 0 deflection, and this is again a 0 deflection, right? But at middle, deflection changes at every point. Okay, the one, the two, but at and at the beginning it's 0. So this is only applied for compliant mechanism. If you are if you are like if you're solving like a simple beam problem, then it won't occur. At simple beam problem, the deflection, the slope is 0 only here, not here. Here the maximum slope here, but plus please remember it's a compliant mechanism. Okay, so yeah, so when you apply these two different boundary condition at x equal to 0 and x equal to L, when you put it like this, you will get C1 and C2. Okay, and your equation look like this one, and again you integrate this stuff, you will get again a one constant c. In order to solve this, you can use another boundary condition, because you see, when you apply a load at the fixed point, the deflection is 0. So at y equal to 0, sorry, at x equal to 0, y will be 0, deflection is 0, right? The next boundary condition is at the beginning of the or at the fixed point. Okay, this is what the boundary condition look like. And so I wanted to ask you what is the calculate the stiffness of the beam. So we will first calculate what is the maximum deflection here. Deflection at the end point. If you so at end point when you put at x equal to L, you will get deflection at the end point. But please do remember that this deflection is only due to this deflection is only due to p by 2, right? F, or f by 2. But we want to calculate the deflection of whole structure, the combination of this, right? So if you look it closely, when you apply a force F, the force will be divided, but the deflection remain constant. So when you bend this stuff, it will bend, both structure will bend like this. Okay? Look like this. So both this point and this point, deflection remain the same. So the deflection of whole structure will also remain the same, right? So the deflection will remain the same as FL cube by 24 by A. Okay, so this is what you get. Please do remember this, okay? And yeah, this is how your beam look like for a compliant mechanism. It's like bending like this, and something like this. Is that and so if you have this deflection, you need to calculate the stiffness. For stiffness, like F by Y, right? Just do this stuff F by Y. This is what the deflection is, and just calculate. I mean, I inertia, moment of inertia, for a long beam is WT cube by 12. You get the answer. So let's just move on to the next question, which is the extension to our previous problem. So if you have the stiffness, using the value of stiffness, calculate actuation for needed to move a mass of 5 kg. 5 mass to move a mass by 5 mm. Okay. So they are asking about the actuation force move this mass by 5 mm. It's a very simple problem. So if you have thing like you have this y equal to FL cube by 24 EI. Okay. So if you have a mass of what was it? You need to calculate actuation force, right? They wanted to know actuation force, and they know at what force the actuation is. So you just need to put y equal to 5 mm here, and you just calculate f force. Okay. So what they have done here. This is what the know. The next question is one of the interesting question. They're asking about next. You would like to use the system as a weight balance. Okay. So instead of F, they will put some kind of a mass. Okay. Some mass, some mass. Okay. And if the encoder uses to measure displacement at the resolution of 1 micron. So if we put some kind of a mass here, it is moving, right? It's deflecting, and that deflection is measured by some kind of a encoder. Okay. Which has a resolution of 1 micron. It can measure a smallest, what is the smallest change in smallest increment it can measure is 1 micron. What would the resolution of weight balance? So like a force and mass. Okay. So here if you see that they have given you the deflection smallest resolution 1 micron, and they wanted to know what is the smallest mass resolution. Okay. So if you see this, if you see this, force is proportional. Let's forget L because L remain the same. So Y is proportional to F. Okay. So whatever will be the increase or increment in Y will remain same. All length and E and I remain the same. Whatever increment in Y will reflect in F also, right? That's what I'm saying. So they wanted to know if the deflection 1 micron, what will be the mass change. So this is what they have done. y is equal to 1 micron, just put it there. So it can measure up to this 5.824 10 to the power minus 4. So when you just convert to millinewton, so it can measure smallest for 1 micron, it can measure to 0.5824 millinewton. This is how small your mass system can measure. How to solve this kind of a question. I think this for solving. So I'm solving this question so that you can solve this kind of a question. So there are problem like this one. This is a compliant mechanism, but you need to just simplify this problem to solve this kind of a problem. Yes, you simplify this problem, solve further. Okay, and you can see that what kind of a beam theory is used for the compliant mechanism. There is one more which is Cherenkov beam. When that is used, you need to know this. And so this is what a series parallel problem, I would say. So this is it, and let's move on to the next question. So this is a multiple choice question. So you can see here kind of a graph is range versus resolution graph. Okay, and you need to guess what kind of actuator lie in the region. So A region is where like you will get a very fine resolution, very small, and you will get a very small range. Okay, and so this is where the problem and this. So what you need to do is that you need to pick this, you need to match this. Okay, so what will be A? Is it piezo actuator or is it something driven motor? So in order to do this, you need to know how this different mechanism work. Okay, so let's just go to the piezo actuator part. The piezo actuators are, I mean, you know that these are like driven by property of physio material, right? These are like one of the what I'm looking. This is a physio. So you don't need actually. So what you just need is like just need some kind of electrical actuation and it will actuate. The property of material. It's a physio history material, right? Just need to, so this is very you. I mean, you have already know that some the physio actuator are used by that HDD arm of the hard disk, right? These are very uh, sensitive equipment, right? So how to so this is where you need to put your minds on. So from I mean the first option, I mean I think these are straightforward. I mean it can I mean cannot measure up to a high range because if you not to do a high range material, the material has to be very large and very difficult to make the material. The physical materials are very less in nature, so you can't expect up to a large range. These are only used for a very small range operation, which is can measure up to 100 micrometer, and the smallest it can measure is 110 nanometer. Okay, let's come to the second problem. So second problem, I will come to it at the last. Okay, let's just move. Okay, I can use. Third, I will move to the last. Okay, so second is compliant mechanism voice coil actuator. So the voice coil actuator. I mean, I think you have already used this thing, right? Uh, for voice coil actuators. So where these voice coil actuators are used, compliant mechanism. These are being used in uh, we are using something like is so I just forgot one. Video actuators are like these are being used for the CD-ROM drive. I think. Sorry, voice coil actuator has been used for hard disk drive. Video actuator, I think you have already know that you have this can move like this. If you open that the hard drive, you have that piezo actuator, and this can move up and down. So it don't have so this piezo actuator doesn't have any friction and backlash, due to which it can measure up to a to a very fine resolution like 10 nanometer. This is what a piezo actuator. So this is what a piezo actuator can be used. And if you go for B option, so B is like in between. Uh, like it can measure up to high range, but it still can have that small resolution. This is what B option refers to. Compliant mechanism with voice call actuator can do that. Okay, can measure a high actuator. So this is being used for this hard disk drive that we have used it. Then coming to the belt drive with motor. Okay, and belt drive with motor are those equipment where I think five and okay. So there are options like D, E, and E and F. Okay, so E and D, if you see, D has a good resolution, which is fine resolution, and E has very coarse resolution, right? So if you see belt drive, why we use belt? So belt are used for transmission. Like it can transmit a load like from a very small point to a big point. Okay, but the problem with belt is it has some kind of friction loss is there, due to which you will see not friction loss, but it kind of suffer from a slippage. Okay, so there might be uh, so you don't get up to that much resolution. But the good thing about belt drive is that you can transmit motion from one point to any other point. Okay, it has a good range, but it don't have that high resolution. Okay, so you see this, so it has a due to slippage problem. I think F will be a right option because the resolution is very bad because of the friction. But if you see that it has a higher range. If you go for the ball screw and lead screw, so ball screw are better than lead screw. I think you must have known that. And lead screw, you don't have a problem of something called friction slippage, right? But it has a problem of friction. So it will be, I think, six. Lead will be six, and the E and you, okay, so this is how you to solve that kind of a problem. So I think E option here is right, and the other option is six. Sorry, second option, the compliant mechanism. So the compliant mechanism is that mechanism, I think, which you have used seen in your CD-ROM drive. No, not. Yes, compliant mechanism you have seen it, but I'm talking about dual actuation. Dual actuation you have already seen it. This is the gross and fine positioning. So for fine positioning you have used piezo actuator, right? And for gross positioning you have used, I think, some kind of a stepper motor, I think. So it's a combination. So in order to capture the ray is coming from which is coming after reflecting from the CD drive, you know that uh, for the fine positioning you are using that kind of a piezo actuator, and for that gross positioning you are using stepper motor or a BLDC motor. This is how you take the advantage of both of them. So C is the one actuator which you are looking for, which has a high range also, and it has a very fine resolution. C is the, so C option, which is C. C is the, C will be right option. Okay, dual actuation part. This way you need to solve this kind of. So coming to the last question here. This question was asked, I think, last year for the problem which I think you must think. So I think I will just say, so this problem, if you see, this problem was asked last year. Okay, so please remember. So you have this whole mechanism here. Okay, the same mechanism as you've seen in sorry. If you have any questions, please do ask me. I'm sharing the screen. This have any just so this is the last question. To determine the stiffness of the mechanism, I am giving you the so this is the mechanism here. This has been fixed here, and consider it a compliant mechanism. So these are the that thick bars you see, and this is the kind of the mass, the slab mass. So it's like the same mass, but you can see that there are like multiple multiple arrangements are made in the similar manner, kind of a squares. Okay, it's like they have made like a square, but two squares are combined like this. Same and these are the fixed block. The dark one are the fixed block, and you are applying mass m here. Okay, so what will happen due to this force apply? You apply like this. Uh, so there will be some kind of a deflection. So I think if you apply something like this, the whole body will move like this. Something, some kind of a deflection will happen here. Some small deflection, and they wanted to ask determine the stiffness of the whole mechanism. Okay, and if it's saying that the stiffness of each individual beam, if there are 8 beams they are showing, so Young's modulus is given here, I is given here, area of each beam is given identical. That shows only bending. So here there is one thing. So I is the moment of inertia, and area of the each beam, all identical. All beams are identical, and assume that beams undergo only bendings, no axial deformation or buckling. So here all these beams are only bending. Okay. So if you apply some kind of a force here, there is no buckling, there is no some kind of actual. So if you apply something force like here, it will deform, right? It will compress. But it is given that assume that there is no deformation or buckling. So please remember this statement. Okay? So there is only bending occurring. Okay. So what? So how many beams you see can go for bending? So you can see these beams, these are like actual forces. So there won't be any bending here because the force is applied like here. There is a one beam because it can bend like this. 1, 2, 3, 4. Okay. Then there is another beam which is 5 here, and then there is 6 beam, 7 and 8. There are only 8 beams which can go for the bending. Okay. So you need to find the stiffness of the beam when each beam stiffness is given like this. Okay. So and your option is definitely like this. So here how to like approach this kind of a problem. Okay, so you know that when you have one beam, so it's like a series or parallel kind of a problem. Okay, you need to see, like suppose if you see this beam. Okay, so I'm considering only this beam like this, and you see if you apply the a force like this one, is yeah. So if you apply something force like this here, which is F here, and this is, so you know that the stiffness, what will go, and how you know the formula, right? Stiffness, which I've already told you, like how to calculate, which is FLQ by 24 EI. You know that, thing like this. So when you know this, and the deflection, this beam will occur, will have the same deflection, because, and the same this beam F beam also will have the same deflection because all the beams are corrected. So the deflection or the bending. So this I'm talking about this part. Talking about this part, delta. So the delta remains same for all this 1, 2, 3, 4, 5, 6, 7, 8, all beams. The delta remains same for all that. Okay. But right, but the mass, but this force will be distributed. Okay. So why am I saying this? So if you remember in your elementary level, there is something called series and parallel problem, right? So if you have this two strings are connected in the series, which has K1 and K2, and the mass is this, right? The mass is here remain the same, right? Or like suppose like a force is here, the force remain the same, but the deflection will be delta 1 plus delta 2. Here you've seen something like K1 K2, something like that, K1 plus K2. So this is what the effective stiffness of the spring will look like. If you consider a same a parallel problem, if you have K1 and if you have K2, something like this, right? You have something like force F applying like here. Okay. So in this case, delta will remain same, right? Because this point will go same manner, right? The delta will remain same, but the mass, or the force will be distributed. Okay, so it's the same case as that. Okay, and if you see this, the effective stiffness will be K1 plus K2, right? Thing like this. So here also it will be K1 plus K2 plus K3 plus K4 plus K4 plus K. So it's like all stiffness will be added. So here there are like 8 beams, so it will be 8K. Okay, like that. Or the other thing which we can do is to solve this kind of problem is you can just go with the same method. Okay, so if you have some kind of a F here, okay, so if you have suppose like if you have applied some kind of a force, so what you need to do is like just distribute that force into F by 8. I think if you distribute into force, so this is something like that. When that mechanism, you can use this formula. So y is equal to, you know, that kx. Okay, k of each beam has given to you. Yeah, y equal, not y equal, y is equal to F by k, right? So I'm talking about each beam, deflection on each beam. Okay. So the force will be distributed here, right? If F is applied here, then consider only one beam, then it will be F by 8, right? Then F by 8, and the stiffness is given to you, which is 12 by Q. You do this, you will get FL. You will get something at FL cube by 96 EI. What you will get, and when you just divide it by Y, so 96 by, or what you can do is 12 into multiplied by 8, 96 EI by L. Here the answer will be 4 years. Okay. So in this manner, you need to solve this kind of question. The last problem. Okay, I've already took 45 minutes. So yeah, so this is in this manner you need to solve this kind of problems, and I think you can easily solve this kind of a problem. Okay, so please solve it, and the problem else. But so I just give you some heads up regarding week 4. So week 4, you see this week 4 problem. So there is a problem. I think this is related to ADC and ADC modules and digital modules problem. So you can see, please, I will solve some of this problem, but please, from week 4 onwards, most of the problem you will get is uh, or logical based problem, or a numerical based problem. So you can see now you can, I think, also expect something related to this. Uh, you need to answer it numerically. The numerical to solve problems. So from this week onwards, I uh, would suggest you to please be serious now, because now the electronics part is coming up, and from week 5 onwards it's going to be. So please, I would for week 4 I would suggest you to uh, go through those books which Professor Gandhi has told you. Okay, because these problems, you need to know some basic related to the electronics part. I think if you saw those lectures from Professor Gandhi, uh, Professor Gandhi has already covered the advanced part, but if you have not know what are the basic or the fundamental parts of it, please look back, because if you skip this week, right, then the coming week will be very difficult. Will be very difficult for you. I will. What is the journal for? Okay, Mahima journal formula of stiffness. Yeah, so stiffness. I mean, I think you see in your elementary level, the general formula is to have, I mean, I told you, let's just see if you have this, like, this is a ground here, and you have some kind of a bar, C bar, okay, made up of some, suppose, let's say iron, and you are applying a force here, okay, actual force. You are applying actual force, and I don't know if you remember in your from your elementary school level, according to, I think, F is equal to AX formula. You remember this? This is, I think, the formula is given by, if I'm not, Hooke's law. So this is called a Hooke's law. Okay. So if you apply some kind of a force F, K is the stiffness of that material. Okay. So it's like K is equal to F by X. So K is basically the property of that material. So if you are, let's say you are using iron, and in so iron is like, let's say, first case. So iron has a bigger stiffness when you compare it with some kind of a uh, uh, let's say wooden. Okay, so wood will have low stiffness. Okay, compared to iron. Okay, because we are, so when I'm stating stiffness, stiffness is like property of the material. Okay, basically it changes from material to material. Whereas force, and so due to this stiffness, the x will change. So if you apply some kind of a force like 100 kg force, okay, the force remain constant. Okay, 100 kg force at metal, and let's say 100 kg the same force at a wooden material. So the wooden material will break first, right, because it has a very less stiffness. You say f is remain same, k and x, like k1 x1, k2 x2. Let's say k2 x2 is the stiffness. K2 is the stiffness of wood. K1 is the stiffness of iron. So you know that iron has a higher stiffness, right? If iron has higher stiffness, then the deformation will be also small. This is what the stiffness is actually the property of a material. So stiffness is the basic definition of stiffness is like uh, the unit force applied, the force applied to get a unit deformation. Basically, when you apply x, when you apply some force where the deformation is one. What the definition is. This is what something. So this problem was asked, I think, last year, and I think I will end of bending. Okay, in terms of bending formula of stiffness. Uh, okay, so beam stiffness formula. Okay, so it depends on different. Okay, in terms of bending. So if you see this, uh, take a little long. So beam. Yeah, suppose if you have a cantilever beam, I'm asking about cantilever. So the deform, if you apply some kind of a force here, how much deformation it is being causing. So in axial beam, it's different. I'm talking. So this is a cantilever beam. Okay. So if you have the deformation something like 3 mm, and you apply some kind of a 10 Newton force, deform for 10 Newton force you are experiencing 3 mm deformation, then your stiffness is 10 by 3 mm. So for that you need to calculate what is the maximum deflection at the point where the force is applied, not to calculate the stiffness. This is how you calculate the stiffness here. So this what I will share those. I will share the slides. Yeah, I think where I've calculated. You can see that deflection stiffness is F by Y. That's what I've calculated. Okay. You know the force, you have to calculate deflection, you will get stiffness. How you do. So beam, there are different types of beam, Mahima. There are cantilever beam, and then there is the simply supported. Uh, there's the axial beam which I've told you, and please do remember that it's a the compliant mechanism. So the boundary condition is different here as opposed to what you have. So the boundary condition as opposed to what you experience in your second year BTech problem where a point load has been applied. Take care of that. But okay, I will end the session today. Okay, I will end the session now.